By the way, I'm not Minhao. I'm not the first author. I'm the last author of this paper, and Minhao is my student. The fun fact is the first author and second author has the same first name. It's not a typo, it's just a coincidence. And I want to thank my collaborators from Florida International University for his support in machine learning expertise. Okay, I guess I need to first start from introducing myself, since this is the first workshop for space and satellite security. So actually, I'm from security community because I'm a one-hat hacker. I play CDF a lot in DEF CON, Pontion, and NSA code breaker, and also I'm a speaker in Black Hat, Blue Hat, Linux Security Summit, and all things which define I'm a white hat hacker, and also I'm a system defender because I built lots of protections in the kernel, and some of them already merged to GSExtract's product, and some of them is already in the iPhone that you are using. And also, I'm a security researcher because currently I'm an assistant professor from CU Bodo, and but I'm a noob in space and satellite. And by the way, I'm also a noob in machine learning, so that's why I need a collaborator from another school to help me with the development of the new techniques. Okay, so the satellite communication and eavesdropping. So this on the left side of the slide shows the protocol format of the de facto communication between the space and the ground station, which is a DVB and a GSE. So, and because this is a radio signals is broadcasted, so everyone can eavesdrop on this communication. For example, you can have another radio receiver to intercept the communication between from the satellite to the ground station, or from the ground station uplink to the satellite. So it's not surprising at all, because James has demonstrated in his Oakland paper almost 2 years ago. And so I'm going to show our eavesdropping devices and our settings. So this is our device to eavesdrop on the communication. And the total cost of this device is almost 15 grand. Because some of the devices are, we got some of the devices from some special channels, so it's a little bit expensive. And this device includes some the PCI card, which is to kind of like receive the signals, and I also have a very professional customized KU band antenna, which can do automatic alignment to the satellites that we want to eavesdrop on. And we deployed this device in a suburban area of Metropolis in Asia with more than 10 million population. And we eavesdropped on the spectrum range from 11 GHz to 12.75 GHz, which covers 7 commercial satellites. And so we received in total, I don't know if so we received in total 26 gigabytes signals. And we discovered that they are highly corrupted, and we discovered that the reason because of some environmental factors. The first factor is the satellite activities, which will perturbate the radio signals that we received. And a second environmental factor that will corrupt the satellite communication is some extreme weathers, like rainstorms, snow, and heavy winds, which are at least it's very common in Boulder area. And we also have the third environmental factor that can corrupt the stream is some surface refraction from mountains and large industry infrastructures, for example, the towers in the factories. And the last factor that can influence the quality of the radios that we receive, that we eavesdropped on, is the quality of the antenna, because we use some customer grade products, and the quality of it is really bad. And it's also operated by noobs like me, so we don't exactly how to play it perfectly. So we get some data, but is corrupted. So this is overview of the data that I was dropped. Just some random data, random hexes. And so unfortunately, some of the hexes are corrupted. For example, maybe these bytes, these bytes, or these bytes, or these bytes. And the issue is we know the stream is corrupted because we cannot successfully decode it. But the question is we don't know which bytes are corrupted, and we don't know their correct value, so we cannot decode the whole stream very well. So it's really challenging if we really want to do some practical eavesdropping, do practical passive attacks on the satellite communication. The reason is because in networking communication, we use some traditional techniques, which is called infinite state machine techniques, algorithm to decode the networking packets. But right now, the streams are corrupted. So the first challenge is we don't exactly know where to start decoding, because the header of the streams may start from the middle of somewhere, and where is the start of the entire package, so we don't exactly know. And the second challenge is some critical fields is also like the length field are corrupted. And the traditional finite state machine decoding algorithm relies on the length field to figure out the start of next header and figure out the start of internal packets. But since the length address is length field is corrupted, we don't know how to continue the decoding. And the last challenge is we don't know whether our decoding is correct or not, because the CRC32, which is used for error detection, is also corrupted. So they are almost useless for our decoding. So we use GSExtract, which implements the traditional finite state machine algorithm to decode the satellite streams, and it only decodes 2% out of the total 23.6 gigabytes that we eavesdropped on. And by the way, the GSExtract is a tool implemented in Jam's paper 2 years ago, or maybe 3 years ago. Okay, so if we consider decoding from another perspective, we'll see another way that we can do decoding. So we can see the whole stream can be divided like this. So first we start with BB header, which is the header of the outermost layer in the whole protocol architecture. And the following BB header is the GSE header, which is the middle layer of the whole stream. And the innermost is IB header, which is innermost header, the header for the innermost protocol. And the following IB header is the payload that we really want to get. Because payload includes the application data, such as, for example, some streams, some Earth images, capturing some military bases, something like that. So this is what we really want. And following payload is another GSE header and another payload. And so our solution to decode the corrupted satellite streams is we are going to use a machine learning technique to directly identify all the BB headers, GSE headers, and IB headers from a satellite stream. And if we filter out all these headers, we can obtain the innermost payload that we really want. Okay, maybe I don't have enough time. So this is another way to see how the algorithm works. We first identify BB header, and then find GSE header, and then IB header, and then remaining things are the payload that we want. So I think I don't have enough time, so I need to skip some of the details. Okay, so this is a encode network that we train to do classification, because obviously this is a very traditional, very classic classification machine learning technique. So we first train encoded network to represent the streams, and then we use another two-stage learning framework along with some data augmentation techniques to improve the robustness of the networking of the neural network, and then we use supervised fine-tune to fine-tune the model with some labeled data. So finally, our objective, optimization objective is to minimize the loss function. So okay. So after we build this, use these machine learning techniques to decode the streaming, we evaluate its effectiveness. So we have our training set, our training data and test data. And the training data is the headers that we can successfully decode it using GSExtract, using traditional techniques. And also some other non-headers. Basically, we have 2 labels, right? So in this way, we can do classification, right? And we have 2 out of 3 for training and 1 out of 3. Okay, it's a typo here. So 1 out of 3 to measure effectiveness. And we also evaluate the effectiveness of data augmentation, which is a technique used in our approach. And we train our model over a 100, and we run the whole algorithm over Intel CPU. Okay, so this is effectiveness and robustness of our new tool. So you can see if we set the flip and loss to 1-to-1, and we gradually increase the corruption degree, which basically means like the stream is corrupted to, for example, to 20%. Okay, so you can see, so for the BB header identification, GSE and IB header identification, we perform pretty good. But for GSE header identification, it's not that good. The reason is because the GS header is a little bit relatively short compared with other 2 headers, and the GSE header, the length of GS header is variable. So basically means our machine learning model cannot precisely grasp the features of GSE headers. Okay, and similar results when the flip and not is changed. And we compare with GSExtract. I think I need to skip the technical details here. So basically the conclusion is we are extremely better than GSExtract. And the usefulness of data augmentation is like this. So basically all the details can be found from our paper. Efficiency is basically the conclusion is we are extremely faster than GSExtract. Okay, and the most important page, since it's a workshop, so I'm seeking for collaborations. So one direction may be the satellite onboard system, and I want to thank my colleague Kevin Delford. He has worked for NASA for almost 20 years, and we had a chat, and he told me something about what is inside the satellite onboard system. Basically, have processors, some processors, and some database. And the funny thing is so currently for all the satellites and all the planes, we only have which is called military standard 1553 database. This is the only database bus that I use on satellite. And of course, lots of sensors with vulnerable firmwares. Okay, so that's it for the satellite onboard system. And for the ground station, we also have we also want to get the firmware for the user terminal, and so that we can reverse engineer it and find vulnerabilities. Okay, and this is my email and my Twitter, so you can follow my Twitter and email me if you are interested. Okay.
All right, thank you very much. Let's thank the speaker. Pretty interesting talk. There should be a lot of questions, I hope. Some comments. Okay, then maybe I start with a question. So it seems you went through a lot of work to make machine learning working on like a protocol essentially. In the hindsight, was it worth it instead of like starting to reverse engineer the parts? Was it still like a time saving to actually use machine learning in the end?
Oh, so I mean, lots of things. Like you mentioned like about reverse engineering, right? So even if we are able to dump the firmware, we don't have symbols in that firmware. So we can use machine learning, or to be more specific, ChatGPT to synthesize the function name, which will help us a lot in reverse engineering the whole firmware.
Okay. All right.
And some other application of machine learning in this scenario is like you can communicate. If you can communicate with the satellite, you can use machine learning to determine which exactly satellites that you are talking with. It's also some classification tasks. Yep.
Okay, thank you.
So you started the talk by talking about that you got all this data that you couldn't decode most of it. Do you have any intuition as to why that was the case? Like presumably the receivers that are actually supposed to be receiving this data can interpret most of it just fine. Yeah, what are they doing differently, I guess? Do you have any insight into that?
So your question is about why we cannot get these public resources?
Well, so you started by saying you got this capture, right? And you can decode like 2% of it or something like that. But there's some device that's the target of that transmission that's presumably able to receive it and decode, 80, 90 plus % of it. What are they doing differently that wasn't being done before?
Okay, good question. So why the signals that we received are of such a poor quality? I also want to know that answer, because I cannot do A/B testing because I don't have the products, very professional products, so I can only see the data that are received. But so since I talked with my colleague Kevin, and Kevin told me like it's actually some kind of common sense in their area because the signals does corrupt. But it haven't been like this, such corrupted.
All right, time for more question.
Hi, thank you for the talk. I'm Yan Long from the University of Michigan. So I'm just wondering, you are trying to do reverse engineering here. What specific goals do you have, or do you even have any specific goals when you're trying to do this? Is it like mostly for eavesdropping? And what challenges do you envision when you're doing reverse engineering? Like when you want to dump the firmware, have you already found some like ports on PCB, something like that?
Oh yes, good question. So the goal of our reverse engineering the firmware is to find some, for example, some third-party components in that firmware, commercial off-the-shelf softwares. That's one goal. Another goal is like you can see some design flaws in that firmware. For example, the Starlink's firmware is like this. You have some antenna to talk with the satellite, and you also have another something kind of router that can connect to your app on your phone. So there are no isolation between the two components. So you can use your app to influence the communication between the container and the satellite. Something like that. Design flaws in it. Yeah.
All right. If there's one super quick question, we can still do it. Is that a super quick question? All right.
There's other data buses you can look at, like CAN bus for small satellites or time-triggered Ethernet. And there's a space-specific one called SpaceWire.
Okay, gotcha. Thanks.